If the sun disappeared right now, we would not know for about 8 minutes. Its last light would still cross space. Its warmth would still reach Earth. For those 8 minutes, the sky would lie to us. But here is the disturbing question. Would gravity lie too? If gravity also travels at the speed of light, then Earth should feel the sun's pull from where the sun was 8 minutes ago, not where it is now. And that sounds catastrophic. Because the sun is not standing still, it moves through the galaxy, Earth moves around it, everything is in motion. If gravity pointed toward the sun's old position even slightly, that tiny delay should create a twist in Earth's orbit, a torque, a slow leak of stability. Over millions of years, the solar system should begin to fall apart, but it does not. Earth has stayed in orbit for billions of years. So what is happening? Is gravity secretly faster than light? Was Newton right that gravity acts instantly? Or did Einstein find a deeper rule hiding inside space-time itself? The answer is one of the most misunderstood ideas in physics. Gravity does not travel faster than light. No signal escapes Einstein's speed limit. But planets do not orbit using a simple delayed pull either. The geometry of space-time contains more than a lagging arrow. It carries information about motion, curvature, and change. And when all of that is included, the apparent delay almost disappears from ordinary orbits. So the real question is not, does gravity move faster than light? The real question is, how does space-time keep the solar system stable without breaking causality? Imagine the sun disappeared right now, not slowly, not exploding, not fading, just gone. For about 8 minutes, nothing on Earth would seem different. The sky would still show the sun. Warmth would still touch your face. Daylight would still pour across the planet, because light needs time to travel. The sun is about 150 million kilometers away, so the sunlight reaching your eyes right now left the sun roughly 8 minutes ago. You never see the sun as it is now. You see a delayed image, a ghost from the past. But now ask the dangerous question, what about gravity? If light takes 8 minutes to reach Earth, and if nothing can travel faster than light, then shouldn't gravity also take 8 minutes? Shouldn't Earth feel the gravity of the sun where the sun was 8 minutes ago? That sounds reasonable, but it creates a terrifying problem. The sun is not frozen in space. It moves through the galaxy. Earth moves around it. The whole solar system is in motion. If gravity pointed toward the sun's old position, even slightly, the force would not point exactly toward the center of Earth's orbit. It would be angled, and an angled force does something dangerous. It creates torque, a twist. Imagine swinging a ball on a string. If the string pulls directly toward your hand, the ball moves in a stable circle. But if the string always pulls toward where your hand was a moment ago, the pull is no longer perfectly central. Part of the force begins acting along the ball's motion. That can add or remove energy from the orbit. Over time, the orbit would change. With planets, even a tiny error repeated over millions or billions of years would become catastrophic. Earth should slowly spiral away from the sun, or fall inward, or drift into a different orbit. But that is not what we see. The solar system has remained stable for billions of years. So we are trapped between two facts. Einstein says no influence can travel faster than light, but a simple delayed force seems to destroy planetary orbits. So is gravity secretly instant? Was Newton right after all, or is our picture of gravity too simple? This is where the real story begins. Newton described gravity as a force between masses. Every mass attracts every other mass. The stronger the mass, the stronger the pull. The farther the distance, the weaker the pull. In Newton's theory, gravity acts instantly. If the sun moved, Earth would know immediately. If the sun vanished, Earth's orbit would change immediately. Newton's mathematics worked beautifully. It described falling objects, the moon's orbit, the planets, tides, comets, and eclipses. But Newton himself was uncomfortable with the idea behind it. How could the sun reach across empty space and pull Earth with no delay? What carries that influence? What is the messenger? Newton had no mechanism. He had a brilliant equation, but not a deeper explanation. Then Einstein arrived and made the problem sharper. In 1905, special relativity introduced a rule that changed everything. Nothing carrying information can travel faster than light. Not matter, not energy, not a message, not a change in a field, not cause and effect. The speed of light was no longer just the speed of photons. It became the speed of causality, the maximum speed at which one event can influence another. That means instant gravity cannot be right. If gravity acted instantly, you could use it to send signals faster than light. Move a mass here, and someone far away could detect the gravitational change before light had time to arrive. That would break causality. Effects could appear before causes in some frames of reference. The logic of reality would collapse. So Einstein had to solve two problems at once. Gravity could not be instant, but gravity also could not behave like a simple delayed Newtonian pull, because that would destabilize the solar system. For 10 years, Einstein struggled with this. The result was general relativity. And the first thing it tells us is this: gravity is not a force in the ordinary Newtonian sense. The sun does not throw an invisible rope across space and pull Earth. Instead, the sun shapes the space-time around it. Earth moves through that curved space-time. The orbit is not Earth responding to a simple arrow of force from the sun. It is Earth following a path through a geometry. That difference matters, because space-time geometry is not described by one delayed line pointing from Earth to the sun. It is described by a full gravitational field, and that field contains more information than just position. It contains motion, it contains curvature, it contains how mass and energy are distributed, it contains how the source is moving. This is where the naive paradox fails. The mistake is to imagine gravity like a simple signal that leaves the sun, travels for 8 minutes, and then tells Earth, pull toward where the sun used to be. That is not how Einstein's gravity works. Even in electromagnetism, the same kind of mistake appears. A moving electric charge creates electric and magnetic fields. Those fields do not behave like a simple delayed arrow pointing only toward the charge's old position. The full field includes velocity-dependent effects. When the charge moves steadily, those extra terms cancel the apparent lag in the dominant force direction. So the field can obey the speed limit while still producing a force that, to a very good approximation, points toward the charge's current position. No information travels faster than light. The cancellation comes from the structure of the field. Gravity has a related effect. In the weak field, slow motion limit of general relativity, the sun's gravitational influence includes velocity-dependent terms. These terms are not optional details. They are required by relativity. If you keep only a delayed Newtonian pull, you get the wrong answer. If you include the full relativistic field, the dangerous orbital torque mostly cancels. That is why Earth does not spiral away. The solar system is stable not because gravity cheats the speed of light, but because gravity is not a simple delayed force. The geometry already includes the motion of the source. This is the key point. For a body moving at nearly constant velocity, the gravitational field is arranged in such a way that the main orbital effect points almost toward the body's present position, not simply its retarded visual position. But this does not mean gravity is instant. It means the static or near-static gravitational field is not the same thing as a new gravitational message. There is a difference between an established field and a change in that field. Earth is not waiting every moment for a fresh instruction from the sun. Earth is moving through a gravitational geometry that already exists around the sun and evolves consistently with the sun's motion. But if the sun truly changed suddenly, that change could not reach Earth instantly. The news would travel at the speed of light. This distinction solves the paradox. Stable motion does not create the catastrophic lag you might imagine. Sudden changes still obey the cosmic speed limit. So if the sun could somehow vanish, Earth would not react immediately. For about 8 minutes, both the last sunlight and the last unchanged gravitational influence would continue to reach Earth. Then the change in space-time would arrive. Earth would stop following its former orbit and begin moving along a new path. That is Einstein's answer. Gravity does not act instantly, but the gravitational field of a steadily moving source does not behave like a crude delayed force either. The full geometry cancels the simple lag effect that would otherwise destroy orbits. This is why the solar system can remain stable while causality remains safe. Newton's gravity works so well because, in ordinary slow-moving systems, it is an excellent approximation. It gives almost the same answer as general relativity for planets, moons, and spacecraft. But underneath that approximation, the real machinery is different. Newton's theory says the sun pulls Earth instantly. Einstein's theory says Earth follows curved space-time, and changes in that curvature propagate at the speed of light. That is not a small correction. It is a completely different picture of reality, and it leads to a deeper question. If changes in gravity travel at light speed, how do we know? Can we measure the speed of gravity directly? For a long time, the answer was difficult. Planetary orbits gave indirect evidence, but the cleanest proof would require something more violent than the smooth motion of the solar system. We would need space-time itself to shake. We would need two massive objects to accelerate so violently that they send gravitational waves across the universe. And that is exactly what black holes do.
When two black holes spiral together and collide, they do not merely move through space-time. They disturb space-time. They create ripples in the gravitational field. Those ripples cannot hide behind the near-static geometry of an orbit. They are the change itself. And if Einstein is right, those ripples must travel at the speed of light. This is where the paradox becomes testable. The solar system shows us that gravity cannot be a simple delayed pull. But gravitational waves show us that gravity is not instant either. Einstein's universe lives between those two wrong pictures. Not Newton's instant force, not a delayed arrow pointing at the past, but a dynamic geometry where stable fields guide motion and changes in the field travel at the speed of causality. That is the secret behind the 8-minute gravity paradox. The sun you see is 8 minutes old. The gravitational change from the sun would also take 8 minutes to arrive. But Earth's stable orbit is not being controlled by a naive pull toward the sun's old visual position. It is moving through the full space-time geometry of the solar system. And that geometry is smarter than our first intuition. But the next part is even stranger, because when space-time actually ripples, we can detect those ripples. And when we did, Einstein's answer passed one of the most astonishing tests in the history of physics. The cleanest way to test Einstein's answer is not with a quiet orbit. It is with a violent change. A planet moving smoothly around the sun lives inside a nearly steady gravitational field. In that situation, the full relativistic geometry cancels the simple delay effect that would otherwise point gravity toward the sun's old visual position. But when mass accelerates violently, the story changes. The field cannot remain perfectly calm. Space-time must ripple, and those ripples are gravitational waves. This is where Einstein's theory becomes testable in the most direct way. If gravity were truly instant, then a sudden change in the gravitational field would be felt everywhere at once. If gravity obeys relativity, then changes in the field must travel at the same cosmic speed limit as light. Not faster, not slower in vacuum, exactly at the speed of causality. So imagine two black holes orbiting each other. They are not simply sitting still. They are accelerating around a common center, dragging the geometry of space-time into a violent dance. As they spiral closer, they lose energy. But that energy does not disappear. It leaves the system as waves in space-time itself. The black holes move faster. The orbit tightens. The waves become stronger. Then, in the final fraction of a second, the two horizons merge. The shape of space-time snaps into a new configuration.
A black hole collision is not just an explosion in space, it is an explosion of geometry. And the disturbance travels outward across the universe as a gravitational wave. This is the part Newton's theory could never truly describe. In Newton's universe, gravity acts instantly. There is no need for gravitational waves because the entire universe updates at once. Move a mass here, and every distant object knows immediately. But Einstein's universe is different. Space-time does not update everywhere at the same moment. A change must travel. A disturbance must propagate. A gravitational wave is the news that the geometry has changed, and the news travels at light speed. In 2015, LIGO detected gravitational waves from two merging black holes. The signal was unbelievably small. It stretched and squeezed the detectors by less than the width of a proton across kilometer-long arms. But the pattern matched Einstein's prediction. Two black holes had collided far away, and the ripple passed through Earth after traveling across the cosmos. For the first time, humanity directly detected space-time moving. Not light from an object, not particles from an explosion. The geometry itself. This confirmed the crucial distinction. Gravity is not instant. Changes in gravity travel at the speed of light. But ordinary orbits do not behave like simple delayed Newtonian forces. That is why the 8-minute paradox is so powerful. It exposes the mistake in our intuition. We imagine gravity as an arrow shot from the sun to Earth. If the arrow takes 8 minutes to arrive, it should point to the sun's old location. Then Earth should feel a sideways twist. Then the orbit should slowly destabilize. But gravity and general relativity is not one arrow. It is the local shape of spacetime. Earth responds to the geometry where Earth is. That geometry is produced by the sun's mass, energy, and motion, and in nearly steady situations, it is arranged so that the orbit remains stable. The dangerous lag is cancelled by the full structure of the gravitational field. No signal travels faster than light. No information cheats causality. The apparent instant direction is not a message from the sun's current position. It is the result of a field that already encodes the consistent motion of the source. This is subtle, but it is the heart of the answer. A steady field and a changing field are not the same thing. The steady gravitational field keeps Earth in orbit. A change in that field is what travels outward at light speed. If the sun could suddenly vanish, which is not physically realistic, but works as a thought experiment, Earth would not respond instantly. For about 8 minutes, Earth would continue moving as before. The last sunlight would still arrive. The last unchanged gravitational geometry would still guide Earth's path. Then the change would reach us. The space-time around Earth would no longer contain the sun's old gravitational influence. Earth would leave its former orbit and continue along a new path. That is not Newton, and it is not a delayed force disaster. It is Einstein's geometry obeying causality. This is why the phrase speed of gravity can be confusing. If we mean the speed at which gravitational changes travel, then gravity travels at the speed of light. If we mean whether Earth's orbit points toward a visually delayed sun, the answer is no, because the full gravitational field is not a simple delayed image. The sun we see is 8 minutes old, but the orbit is not controlled by eyesight. It is controlled by space-time geometry, and space-time geometry is richer than a light beam. This also explains why Newton's theory works so well. For slow motion and weak gravity, general relativity reduces almost exactly to Newton's law. The differences are tiny in the solar system, except in precise cases like Mercury's orbit, GPS timing, and gravitational waves. Newton gave us the correct practical rule for most ordinary situations. Einstein gave us the deeper machinery behind it. Newton said gravity is an instant pull. Einstein said gravity is geometry, and changes in that geometry propagate at a finite speed. The difference matters most when gravity changes quickly. A planet orbiting quietly does not reveal the full drama. Two black holes colliding do. That is why gravitational waves are so important. They are not just another prediction. They are proof that gravity is dynamic. Space-time can carry energy. Space-time can ripple. Space-time can transmit information from one part of the universe to another, but it cannot do so faster than light. This protects causality. If gravity were truly instant, we could in principle use it to send messages faster than light. Shake a massive object here, and someone far away could detect the gravitational change immediately. That would break the order of cause and effect. In some frames of reference, the effect could appear before the cause. The universe would become logically unstable. Einstein's theory avoids this. It keeps the solar system stable without allowing faster-than-light messages. That is the genius of the solution. It does not choose Newton or the naive delay picture. It rejects both. Gravity is not an instant invisible rope. Gravity is not a simple signal always pointing to the past. Gravity is a field of space-time geometry whose steady part guides motion locally, while changes in that geometry move at the speed of causality. That is why Earth does not spiral away from the sun. That is why the solar system survived. That is why gravitational waves arrive as real traveling disturbances. And that is why Einstein's view is so much stranger than both common sense and Newton's picture. The universe does not need gravity to cheat. It needs our picture of gravity to grow up. The old question asks, does gravity travel faster than light? But the better question is, what exactly is traveling? A force, a message, a change, a ripple? The established geometry around the sun is already part of the local structure Earth moves through. But if the sun changes, the update to that geometry must travel. That update is limited by c, the speed of light, the speed of gravity waves, the speed of causality, the fastest speed at which reality can inform one place that something has happened somewhere else. So when you stand under sunlight, you are seeing the sun from the past. When you feel Earth held in orbit, you are not receiving an instant message from the sun. You are living inside a space-time geometry that has been shaped by the sun and evolves according to Einstein's equations. And if that geometry changes, the news does not arrive early. The universe waits 8 minutes for the sun, years for nearby stars, billions of years for distant black hole collisions. Every influence has a travel time. Every change has a horizon. Every cause must earn its way across space-time. That is the rule Einstein protected. And now the paradox disappears. Gravity does not outrun light. Earth is not pulled toward a crude 8-minute-old sun. The solar system is stable because general relativity includes the full motion-dependent structure of the gravitational field. The speed limit remains unbroken. Causality survives. And Newton's instant force is revealed as a brilliant approximation, not the final truth. The next time someone says gravity travels at the speed of light, remember the hidden detail. They are talking about changes in gravity, ripples, disturbances, updates in space-time geometry. But the steady field that guides an orbit is not a series of delayed arrows flying from the sun. It is the local geometry through which Earth moves. That is why the sun can be seen as a ghost from 8 minutes ago, while Earth's orbit remains stable now. The sky shows us the past. Space-time gives us the path. And gravitational waves prove that when the path changes, the news still obeys the speed limit. That is the real answer. No faster-than-light gravity, no broken Einstein, no impossible torque tearing the solar system apart. Just a universe more elegant than our first intuition. A universe where gravity is not a rope, not a pull, not a shortcut through causality. It is geometry, and geometry changes at the speed of light. If this changed the way you understand gravity, subscribe to the channel and comment below what feels more surprising, that gravity changes travel at light speed, or that Earth's orbit stays stable because space-time is not a simple delayed pull.